And today we have an Amol Aggarwal, and he's going to talk about fusion. Thank you, everyone, for coming.
Okay, thanks, Slava, for the introduction and the invitation. So, I mean, this is going to be, by and large, an expository talk on the notion of fusion, which is a 40-year-old concept. So, if you were looking for, the most recent advances, I'm not going to describe them to such a great extent. So let me just get started. So, okay, so what is fusion? So fusion, by and large, is a way of producing new solutions to the Yang-Baxter equation, starting from an initial one. And it was introduced by Kulish, Reshetikhin, and Sklyanin back in 1981, so almost 40 years ago by this point. So why would one want to do this? I mean, okay, so there are a number of reasons why one would want to fuse. I mean, we all know the power of solutions, having solutions to the Yang-Baxter equation. But the point is that so if I take even like the most oldest, most basic solutions to the Yang-Baxter equation, 30-year-old solutions, 35-year-old solutions, the weights that I get from fusing them, from just applying the fusion procedure to them, often give rise to very important and well-studied special functions or probabilistic systems. That people actually still, a lot of people, members of the audience still study today. For example, I mean, this is a very non-exhaustive list, but you get various versions, modified supersymmetric, non-symmetric versions of the whole Littlewood polynomials, factorial Schur functions, LLT polynomials, McDonald polynomials, p-adic, metaplectic, Archimedean, cutiform, Whittaker functions. I mean, there's a huge list there's a huge range of what you can get by fusing even the most basic solutions to the Yang-Baxter equation. So a second reason why you might want to fuse is that fusion gives you, the fusion procedure gives you a number of parameters to play with. And once you have these parameters, you can use them to actually study sort of unfused systems. I won't talk about this. Actually, in the first talk that I gave back, I guess a year and 3 months ago, I had mentioned this in brief, that sort of once you have some sort of 6-vertex model, you can write down Cauchy identities with it with respect to a fused model. So I mean, you can sort of gain information from unfused systems using a fused model as sort of a way to extract information from it. A third reason is that once you sort of start from an initial once you sort of start from an initial seed solution, so to speak, and you start fusing them, you kind of know that all the fused weights are related, which tells you that all of like sort of the functions that you get from them, say, are also related in a sense. So using this, you can kind of identify relationships between a priori different, seemingly different families of symmetric functions. So for example, you can see quickly, plethistic relationships between symmetric functions, which I'll very briefly mention. Things that I don't mention include transition coefficients between families of symmetric functions. So for example, I mean, you will be able to identify, I mean, using fusion, you can start to identify coefficients when you say expand LLT polynomials over the whole Littlewood basis. I mean, fusion allows you to see representations for the coefficients that arise from such a procedure. You can also see relationships between various types of stochastic processes, such as say like the ASEP and the TASR, the zero range processes. Yeah, so you can identify relationships between sort of various specializations of fusion of these fused models. Okay, so with that said, I guess I sort of want to get started on explaining how fusion works really. Okay, so let me start by, as I mentioned before, fusion is a way of producing new solutions to the Yang-Baxter equation, starting from an initial one. So I'll start with an initial solution to the Yang-Baxter equation, which is over here. Okay, so over here, I've drawn probably the most basic solution to the Yang-Baxter equation. It's the EQ-SL2 hat solution, the fundamental one. So it's like the 6-vertex solution to the Yang-Baxter equation. So the vertex weights are shown over here. I mean, there are 6 vertices. There's sort of the empty vertex, which has weight 1. The full vertex has weight 1. This double vertical has weight q times 1 minus u over 1 minus qu, and u and q are 2 parameters. double horizontal has weight 1 minus u over 1 minus qu, and the two corners have their weights. Okay, so this gives you a family of weights, and these weights can be arranged in a matrix, 4 by 4 matrix. So this R of u, I1, J1, I2, J2 denotes the I1, J1, I2, J2 entry of some 4 by 4 matrix, and the weights are given by this. So there's 6 non-zero entries in this matrix. This gives you some R matrix, and this R matrix satisfies this Yang-Baxter equation that I'm sure basically everyone in the audience has seen before. Okay, so in terms of the entries, you can write it, and you can. This is a matrix equation. You can write it in terms of the entries, and when you write it in terms of the entries, you get an equation that looks like this. So I'm just taking the one specific entry of this matrix, and you'll get of this equality, and you'll get something that looks like this. And this has this sort of diagrammatic interpretation, which I'll be using fairly frequently, as follows. So R y over x, I1, J1, I2, J2. So y over x, I view y and x and z as parameters associated with the various lines in my vertex model. So for example, here I have one line which has parameter y, here I have another line which has parameter x, and here I have another line which has parameter z. And this u will be the quotient of the vertical line divided by the horizontal line. So this r y over x, the vertical line, I mean, okay, you have to tilt your head a little bit, but the vertical line is y and the horizontal line is x. And I see that I have I1 coming in vertically, J1 coming in horizontally, and I2 coming out vertically and J2 coming out horizontally. Likewise, this is RZ over X. So I have RZ over X. So I'm looking at where this line intersects this line. So this is K1, J2, K2, J3. And the last one is RZ over Y, K2, I2, K3, I3. Okay, so this is a fairly standard way of diagrammatically interpreting equations like this. And of course, since I have a product of matrices, I end up summing over the 3 indices I2, J2, and K2, which means that I sort of sum over this dashed triangle. So I'm fixing the boundary conditions, and I'm summing over all possible things that can happen in the interior. So that's on the left side. On the right side, I have a similar sort of diagram, which looks fairly similar, except now I sort of pushed this line, the Z line, over to the left of the cross. And I get something that looks like this. So, I mean, the Yang-Baxter equation, sort of informally speaking, tells me that I can push lines through crosses, and that doesn't change partition functions. Okay, so far I've just talked about the fundamental solution to the Yang-Baxter equation, but I want to now get new solutions from this fundamental one. Okay, sorry. Okay, so it seems that I skipped a slide, but the slide that I skipped is over here. So again, yeah, these are the weights. As I mentioned before, you assemble an R matrix out of it, and this R matrix is the image of the universal R matrix for UQSL2 hat under its fundamental or defining representations. It's basically probably one of the oldest solutions to the Yang-Baxter equation. So one often defines this vector space Vm, which is V1 tensor V2 all the way to tensor Vm, where these VIs are spanned by E0 and E1. E0 you should view as sort of the empty edge, and E1 is the full edge. Okay, and you can interpret basis elements as just a series of tensors as pure tensors, and you can view them as sort of states where an E1 has a vertical arrow and an E0 has no arrow. So like E1 tensor E0 would have a vertical arrow and then 2 empty states. Okay, so this is right. And as I just mentioned, this satisfies the Yang-Baxter equation. Okay, so now I want to create new solutions from this fundamental one. So let's fix row parameters and column parameters. We'll call them, they're often called rapidities, x1, x2 all the way to xl, and y1, y2 all the way up to ym. Okay. And we'll fix some sequences, A1, A2 all the way to AM, B1, B2 all the way to BL, C1, C2 all the way to CM, and D1, D2 all the way to DL. So these A, B, C, and D you should view as parameterizing boundary conditions for the model on an L by M square, okay? So the square that I have in mind is this one over here. So on the bottom, sort of paths enter according to this A this M tuple A. So like if A1 is 1, then I have an arrow entering here, and if A2 is 0, then I have no arrow entering here. Likewise, B is indexing the boundary condition along the left boundary, C is indexing it along the top boundary, and D is indexing it along the right boundary. Okay, and I'll define the bundle. I mean, I'm kind of making up this notation. I don't know of I mean, this is really just a product of R matrices. I don't know if there's a real word for it, but I'll just call it sort of the bundled weight, because I'm kind of bundling a bunch of these lines together as the partition function of this model here, of this rectangle over here, where at coordinate I comma j, I use the weight that's obtained from these weights, these R weights, where the spectral parameter u is given by the spectral parameter in the jth column, or the ith column the ith column divided by the jth row. So y, actually these are going in reverse direction, so it's y m minus I plus 1 over xj. So that's the u, and then the so we use that as the spectral parameter in the ith row in jth column. Okay, so this is just some partition function, and you can view them as the elements of the entries of the R matrix for UQSL2 hat under a tensor product of fundamental representations. So again, I'm just calling this the bundled weight. Okay, so somehow I skip 2 slides whenever I press the space button, which is kind of strange. I'll try not to do that. Anyway, so the point is that these bundled weights satisfy the Yang-Baxter equation. This is not a very deep fact at all. In fact, it's probably more visible by just taking a look at the picture rather than the equation. So if I can stack 3 bundles, I can kind of construct the analog of this picture over here by just creating sort of L, X lines, M, Y lines, and N, Z lines. So I get something that looks like this. And the Yang-Baxter equation, 1 by 1 at a time, tells me that I can move each Z through the crosses, and I'll get a picture that looks like this. And if you think about it for a moment, this is precisely the statement that these bundle weights satisfy the Yang-Baxter equation. Okay, so I mean, okay, so this is one way of, okay, if you want to know what the Yang-Baxter equation looks like in terms of our matrix elements, here is the formula. I mean, it's fairly close to the one I had before. The ZXY of I1 sort of here, J1 over here, then I have I2 over here and J2 over here, and then I have the Z on the Z of XZ of K, J, K, J, and then you keep going. So this gives me a solution to the Yang-Baxter equation coming from these sort of bundle weights. Now, the issue with this solution, which is one reason why we're often fairly hesitant to use it, is that the state space for these bundled weights are huge. Okay, so recall if I go back, A is an M tuple and B is an L tuple. So in particular, that means that the state space along the vertical direction is 0, 1 to the M, which is 2 to the M dimensional, and the state space in the other direction is 0, 1 to the L, which is 2 to the L dimensional. So this is troublesome for 2 reasons. First of all, it's fairly big, and remember, sort of at the end of the day, what I want is for these guys to be enumerating partitions, but I'm more like enumerating M or L tuples of partitions from this procedure. It's even worse because I often want to analytically continue on M and L. I want to send them to infinity, or I want to even make them complex numbers or something like that. If the state space depends on M and L in this way, it's not at all obvious how to do that. Okay, so I want to somehow compress the state space of this model. And before doing that, I just want to mention that as sort of an exception. I mentioned that the state space is unmanageably large. It's almost always unmanageably large, and I only know of one exception to when it's sort of manageable, and this comes from these works of Brubaker, Buscema's, Bump, and Gustafsson. So if the seed solution is very simple, so even simpler than the ones I just wrote down, to what they call these monochromatic weights, then I mean, if these seed solution is extremely simple, then the bundle weights can be fairly manageable, and that's actually what they use to construct their Iwahori-Whittaker functions and their metacollectic Whittaker functions. But by and large, even if I go to say these weights over here, the state space is going to be a total disaster if I try to do Okay, so I want to describe a way of compressing, and this is really the fusion procedure, as a way of sort of compressing or sort of projecting or restricting to a smaller state space that's more manageable and that will give me friendlier widths. Okay, so as I mentioned before, sort of the issue with bundling is that the bundled R matrix acts on too high dimensional space. So I mean, the basic idea is a fairly natural one, is that you restrict the state space by restricting the R matrix to some lower dimensional subspace. So you have to find some lower dimensional subspace that's fixed, that's closed under the action of the R matrix, and that will be sort of the state space that you use instead. Okay, so to construct the space, one has to make a few choices. So you have to make a special, so this is the simplest to set up for special choices of these parameters x and y. And it turns out that the easiest one, or at least the one that I'll describe in this talk, is to set x and y to be geometric progressions. So with ratio gamma. Okay, so like x is x gamma, x squared, x gamma squared, x gamma cubed, all the way to x gamma to the L minus 1, and y is y gamma squared, all the way to y gamma to the M minus 1. And now I need to pick my gamma properly. Okay, and the basic underlying rule that tells you how to pick gamma is you pick gamma so that the R matrix that intertwines, I mean, the R matrix that I had from the first slide is a projection. Okay. So in particular, I can pick, if I go back to the R matrix, it has 6 entries, and if I plug in gamma equal to Q, you'll see that the R matrix looks like this one over here, which is indeed which you can sort of quickly, which you can verify is a projection. So its image actually consists of what are known as Q-symmetric tensors, namely tensors that are sort of this form. I sum over all index sets I, and I look at Q to the number of inversions in I times VI1 tensor VI2, etc. So maybe the most basic example of this is that I take K equal to 2, in which case an example of a Q-symmetric tensor is V1 tensor V0 plus Q times V0 tensor V1. Okay, so this is, so yeah, okay, so okay, so now as you can see, this space of Q-symmetric tensors, it's of dimension k instead of 2 to the k. Namely, it's, I mean, if I just know how many V1s are in any Q-symmetric tensor, I pin down the Q-symmetric tensor formula. So it's or at least sort of any pure Q-symmetric tensor is determined by the number of V1 components in it, which makes this whole space of dimension the space of Q-symmetric tensors of dimension k instead of 2 to the k. So this is indeed a much lower dimension. So I should just quickly mention, although this will not really be a topic of this talk, that this projection property also holds if this parameter gamma is equal to 1 over q, in which case the image is spanned over the space of antisymmetric tensors or wedges. This gives rise to another form of fusion, like a sort of a fermionic or antisymmetric form of fusion, in which the weights satisfy an exclusion, sort of an exclusion condition that allows you to have only one arrow of any color along an edge. I won't make a big deal out of it. The only reason I mentioned it is that gamma equals 1 over q is indeed another point that for which the R matrix is a projection, and you can also apply the fusion procedure there, although I won't do that in this talk. So as I said, I want to outline sort of an explanation of, or a description of what fusion is in the case when gamma is q, and that will hopefully give you an idea of how to implement this if you so desire. So right. So okay, so what we're going to do is we're going to set gamma equal to q, and then we're going to more or less play the same game as before. We're going to look at these bundled weights. So I had these A, B, C, and D as before that index my boundary conditions for this L by M rectangle. And now the only difference is that now I'm specializing my parameters x and y. So so as I said before, y goes in this geometric progression and x also goes in the geometric progression. So due to the indexing, y is being multiplied by a factor of q every time I go to the left, and x is being multiplied by a factor of q every time I go. Okay, so these zxy weights, as I mentioned before, these bundled weights satisfy the Yang-Baxter equation, but I want to sort of project, in a sense, the space of to the space of Q-symmetric tensors which diagrammatically more or less is encapsulated in the following definition. So let's fix some integers a and b, and I'll define this partition function, this sort of partition function z xy of sort of this Roman AB and this frac CD as the sum of this q to the inversions of this sort of all tuples A, which have exactly Roman A number of ones, and plus times q to the inversions of B. So this of B, where I'm also summing over all L tuples B that have this sort of Roman B number of ones, and then I multiply by these bundled weights. So it's sort of a q-weighted linear combination of these bundled weights. Okay, and sort of you can view this, if you want, as taking the R matrix associated with this bundled weight and projecting or restricting it to the space of q-symmetric tensors. So I mean, you will indeed get some sort of q-weighted linear combination of these bundle weights if you do that. Okay, so this is my zxy. So are there any questions so far? Okay, then I guess I will keep going. Okay, so now these weights that I've just defined, they satisfy a number of fairly useful properties, maybe the main one being the notion of this Q exchangeability. So let's say I have a permutation C prime of C and another permutation D prime of D. So they have the same, so C prime has the same number of ones as C and the same number of zeros as C, except they're just permuted slightly. And D prime has the same number of ones as D, but again, they're permuted. So the statement is that Z of, again, this Z that I just defined, in this C prime and D prime are the same as the C and just the Z and just CD up to certain factors of Q. Okay, so up to certain factors of Q, what this is telling me is that the Z ABCD doesn't depend on which permutation of C and D I pick. I mean, it only depends, in particular, it only depends on the number of ones contained in C and the number of ones contained in D. So more specifically, if you reverse Ci and Ci plus 1, that only changes Z by a factor of Q or 1 over Q, which is why we sometimes refer to this notion as Q exchangeability. And the interpretation, again, sort of the linear algebraic or representation, theoretic, if you like, interpretation of this is that it's basically saying that Q symmetric tensors are closed under the action of this bundled R matrix. I mean, yeah. So I mean, you can sort of convince yourself, if you wanted to write down in linear algebra in terms of the R matrix what all this meant. It's basically saying that that the sort of bundled R matrix leaves the space of Q symmetric tensors closed. Okay, so I'll explain a proof of this lemma in a few slides, but let me just mention for now that it will follow from the Yang-Baxter equation, and it will crucially use the fact that R of Q is a projection. Okay, but again, let me table that for now and define the fused weight. So for any integer C and D, so now these Roman C and D are integers instead of sort of tuples. I'll define this fused weight R xy of A, B, C, D to be Q to the number of inversions in C minus Q to the number of inversions in D times this Z from the previous slide. So times this Z over here. And as you can see, by the Q exchangeability, as long as if I sort of fix the permutation class of these sort of frac C and frac D, this does not depend on my choice of frac C and frac D. So I mean, as long as I fix the number of, say, ones and zeros in these two tuples, it doesn't depend on them at all. Okay, so this is a well-defined notion for any choice of these math frac C and math frac D, which have the correct number of ones and zeros. Okay. So okay, so I can associate now this Rxy of ABCD, which also depends on these two parameters L and M now. Again, the sort of the vertical and the rectangle, the size of the rectangle that I'm compressing. I can view this as a vertex it will have sort of row rapidity parameter x and column rapidity parameter y. And I'll also say that it has row spin L and column spin M. So L, you can be, so the spin is the number of columns I'm compressing, and M is the number of rows that I'm compressing. Okay, so in particular, it has like 4 parameters now. It has X, Y, L, and M. It also has Q. So I guess maybe 5. So we can now interpret this fused weight as the weight of an arrow that has A entering vertical arrows, B entering horizontal arrows, C exiting vertical arrows, and D exiting horizontal arrows. It's as if I took this original partition function, I compressed this whole rectangle to a single vertex, and I forgot the orderings of the A's, and I forgot the orderings of all the boundary conditions, and I just remembered how many arrows were entering at each of the four boundaries, but didn't care about their ordering in any way. Okay, so I will often refer to this. I'll often sort of draw these fused weights diagrammatically as sort of having a single vertex, but now I can have multiple arrows entering and exiting through it. And of course, for this to make sense, you'll need A and C to be in 0M. I mean, because my original rectangle, it had M boundary locations, and therefore I could only have between 0 and M entering arrows, arrows entering vertically. Likewise, only 0 through M arrows exiting vertically, and 0 through L arrows entering or exiting horizontally. Although this condition will later sort of be analytically continued and dropped away, but for now this is a condition that's relevant for this procedure. Okay, so I've defined these fused vertices, and of course it would be useless unless they satisfy the Yang-Baxter equation. And the following proposition, which I will again prove a little bit later, shows that they do. So I mean, these fused vertex weights satisfy this equation, which you can sort of, I'll draw a picture for it later on, but this is exactly the Yang-Baxter equation, identical to the previous one back here. Okay, but now with these fused weights. Okay, so I have 2 things that I kind of owe you before I talk more. Well, maybe 3 things actually. So the first is I owe you sort of a proof of this lemma, of this Q exchangeability lemma, in order to make sense of this definition. The second is I owe you a proof of this Yang-Baxter equation. And the third is probably I owe you some sort of explanation of how to compute these weights. I mean, I've given you sort of a bald definition of it, but that wouldn't be so useful unless it actually gave rise to formulas. So these are the 3 things that I'll try to explain in the coming sort of moments. Okay, so let me start with Q exchangeability. So just to remind you, the statement is that if I permute these math frac C and these math frac D, then I only change Z up to sort of an overall factor of Q given by the number of inversions, by sort of a difference in inversions. Okay, so I can prove this by just permuting one pair of entries at a time, right? I can get from any I can get to any permutation of C and any permutation of D by just permuting one pair of entries at a time. So let me actually imagine that C is equal to C prime, and that D and D prime are the same except in 2 entries. So more specifically, I'll assume that DI or dj is equal to dj prime unless j is equal to I or I plus 1. And then I'll assume that di and di plus 1 is the flip of di prime and di plus 1. Okay, and I'll also assume that di is not equal to di plus 1, or else this is sort of trivial. I mean, then both sides are obviously going to be the same thing. Okay, let me also assume for simplicity that L is 2. I mean, you'll see by the proof that this condition is completely irrelevant. It will just make my drawing of partition functions a little bit easier. You can easily extend this argument to bigger values. Okay, so the proof will proceed as follows. So I'm going to attach across. So I'll start out with my sort of bundled partition function, the z, x, y, a, b, c, d. And I'm going to attach across to both sides of it. Okay, so I'll attach across to the left here, and I'll attach across to the right here. And Yang-Baxter tells me that I can attach the cross either way, and I don't change the partition function. Okay, so in particular, what I get is that. So I have, let me sort of parse this equation diagrammatically. So on the left side, I've attached a cross, and this cross has, as we know, this bundled weight due to my choice of x and y, the fact that they lie in a geometric progression. This rapidity is qx, and this rapidity is x, right? I mean, again, due to my choice of the rapidity parameters in this bundled weight, in this sort of bundled weight. Okay, so that means that the spectral parameter at this vertex is the quotient of qx by x, which is just q. Okay, and this is indeed where the rq parameter plays. This is indeed where rq is important. It's because it's really what you get from attaching these crosses. Okay, so I have rq of b1, b2, and then I sum over k1 and k2, and then I have this bundled weight of zxy of a coming from the bottom. Now k coming along the left boundary, c exiting along the top, and then d exiting along the right boundary. So that's the left side. And on the right side, I have I start out with the bundled guy. So I start out with z xy of a, b, c, and now k, which I'll sum over. And then this cross I'm attaching to the right is going to be r. Again, it's going to have spectral parameter q given by the quotient of this guy divided by this guy, qx divided by x. And it's going to have k1 coming in from the bottom, k2 coming in from the left, d2 exiting from the top, and d1 exiting from the right. Okay, so this is so this is just the Yang-Baxter equation. And of course, the important point is that now I have more q's here due to the fact that of the quotient of the spectral parameters at the crosses. Okay, so I've just rewritten the equation over here. And now the property of q that's relevant is that if I plug in u equal to q, if I again plug in the spectral parameter equal to q, then rq of ij10 is equal to q times rq of ij01 for any choice of I and j. So regardless of how I pick I and j, you're going to have this equality, and this is basically the statement that rq projects onto the space of q symmetric tensors. I mean, it's more or less that statement. Yeah, and I mean, it's really the statement that this row is q, this column here is q times this column. So yeah. Okay, so now let's just take this equation and analyze how it depends on d, right? All I have to show is that if I swap two guys, if I swap d1 and d2, di and di plus 1, really, then I gain or I lose a factor of q. Okay, so the left side more or less will give me my partially fused weight. So it will give me the z of xy of abcd, where a and b are now Roman, like Roman numeral, Roman letters instead of these frac letters. So let me quickly explain that. So all I'm doing in this first line here is I'm just summing over k1 and k2. I mean, they can be 1 and 0, right? So and I'm assuming, yeah, so they can be 1 and 0. So I'm just plugging in k1, k2 equals 1, 0, or k1, k2 equals 0, 1. And that gives me this line over here. Now the second line, I'm using the fact that r_b1, b2 of 1, 0 is q times r_b1, b2 of 0, 1, this property. Okay, so I can in particular factor out this guy. This will give me a factor of q over here due to this property, and I'll be multiplying by the z of xy of a01 is my choice of k times with cd. And then the second term is just going to give me this guy over here, zxy of a10 cd. Okay. So now if you look at this, okay, so if you look at what's going on in the parentheses over here, you'll see that it's actually almost exactly identical to my definition of z. Okay, in particular, I'm multiplying by a factor of q whenever this, I'm multiplying by a factor of q, which is kind of counting the number of inversions in B. Okay, the one thing that I'm not doing is I'm not multiplying by q to the number of inversions in A and summing over A, but I am multiplying by q to the number of inversions in B and summing over B. So this till is a little bit of a lie here, but it becomes true the moment I take this left side here, I multiply by q to the number of inversions in A, and then I sum over all A. Okay, so I didn't write that, but pretend that I did. So I mean that's why I'm sort of lying with this tilde here. But if you pretend that I did, then this equation, this equality is basically correct. Okay. Okay, so now the right side only depends on, okay, so that deals with the left side. So basically, if I sort of just take this guy and I sum over all possible A's and I multiply by Q to the number of inversions in A, I get my fused weight up to some factor. Okay, now let me look at or I get my ZXY of ABCD up to some factor, basically. Okay, now the right side, my claim is that it only depends on D through a power of Q. Okay, so let me quickly explain why that's true. So if I look again, so my right side is this guy over here. And now, again, I'm going to use this property, this sort of fundamental projection property over here. And you'll realize that, first of all, the ZXY of ABCK, it doesn't have a D in it. It doesn't depend on D. The only place where I see dependence on D is through this RQ. Okay. And in this RQ, it also doesn't depend on K1 and K2. Or I mean, sorry, up to okay, it does depend on K1 and K2, but only what I should say is that this RQ of K1, K2, D1, D2, if D1, D2 is 1, 0 or 0, 1, I'll only be multiplying my result by a factor of Q, or more specifically, what I have is that RQ of K1, K2, D1, D2 is equal to Q to some indicator event that I have D1 is bigger than D2 times RQ of K1, K2, 0, 1. So basically, all I'm applying is this statement over here. Are there any questions with that? Oh, okay, yeah. So I mean, this statement over here is really a fairly simple consequence of this property of RQ. Okay, and as you can see here, again, this thing in the sum, once I do that, this thing in the sum no longer has any D dependence. This D dependence only came from the fact that I was asking myself whether or not D1, D2 was 1, 0 or 0, 1. Okay, so that gives me only a power of Q that depends on whether or not my D1, D2 was a 0, 1 or a 1, 0. So in particular, what this is telling me is that if I equate the left and the right side now, on the left side up to some summation, gives me my weight Z of XY of ABCD. And on the right side, it gives me something that's independent of D, except for this single power of Q to the indicator event that D1 is bigger than D2. Okay, so that basically tells me that this weight, this sort of Q symmetrized weight, Z of XY of ABCD, is proportional to this power of Q, which is exactly the exchangeability statement. I mean, yeah.
Well, can you just remind us why it's either 0, 1 or 1, 0? Like,
oh, yeah, okay, yeah. You're wondering why it can't be like 0, 0, for example? Yeah, okay, so I cheated a little bit, okay, but okay, so I'm assuming that di is not equal to di plus 1. So that means that, you know, the boundary here, so this D, it's not 1, 1 or 1, 0. Otherwise, it's not 1, 1 or 0, 0. Otherwise, this statement is sort of trivial. I mean, both sides will be obviously the same thing. Now, if K1 and K2 were 1, 1, and or say K1 and K2 were both 1, 1. This weight would be 0, right? Because I have one incoming, one outgoing, one incoming horizontally, one incoming vertically, but only one total arrow outgoing. So basically, maybe a better way of saying this is that this weight will vanish, or this should be a D, D1, D2. This weight will vanish unless RK1, K2, D1, D2, this is a typo, that will vanish unless K1, K2 is 1, 0 or 0, 1. So that's all I need to consider. Does that answer your question?
Yeah, I think so. Thanks.
Are there any other questions? Okay. So that's all I have to say about exchangeability. So now I have to justify to the Yang-Baxter equation, which I'll do next. Okay, so so again, to remind you, the Yang-Baxter equation looks like it's the statement here, which I've kind of drawn schematically over here. So I mean, I have it's almost identical to the the previous one for the UQSL, I mean the fundamental weights, except I now have multiple arrows entering and exiting along the different edges of the model. Okay, so the proof, I mean, on a high level, the proof is basically by applying the Yang-Baxter equation and then repeatedly Q-symmetrizing and applying exchangeability, Q-exchangeability. So I'll do this, and hopefully this is the worst slide in the talk. I'll sketch how this works. Although, I mean, it's not a big deal if you're not really following the indices. I hope to just give you a flavor of what you do. So the point is that, okay, I have a left side, and I have a right side. The left side will be some power of Q times this left side, and this right side will be the same power of Q times this right side. And that'll do the job, okay? So more specifically, the left side of that equation will be Q to some inversion count, basically, times this. And the right side, just do the same reasoning, will be Q to this inversion count times this right side here. Okay, so let me just quickly sketch to you how what one does for one of these sides. Okay, so I'm starting out, okay, so let me start out with these, the left side of the Yang-Baxter equation. So I have R, I'm summing over I2, J2, and K2 of this guy over here. So I1, J1, I2, J2. Yeah, I keep going for the rest of them. Okay, so now what I'm going to do is I'm going to just plug in my definition for R, right? So my definition for R, if I go back, it's back here. It's Q to some power times the Z, and the Z in turn was Q to some power times the sum of Z's, or sorry, the sum of Q to some power times a bunch of bundled weights. Okay. So I'm just going to plug everything in. Okay. And you'll get something like this. I mean, you'll basically get Q to some inversion count involving I1, J1, I2, J2 times this bundled weight times Q to another inversion count time involving 4 guys times the bundled weight involving these 4 guys, and one more term like that. Okay, and what you can see, and now you're summing over basically everything. But the main point to realize is that you have all of the sort of interior edges, the J, anything with the 2 as a superscript will cancel. This inversions of J2 or I2 will cancel with this inversion of I2 here. This inversion of J2 will cancel with this inversion of J2. And this inversion of K2 will cancel with this inversion of K2 here. So I'm left with this power of Q. It will only be an inversion count involving I1, J1, K1, and I3, J3, and K3, which are fixed, right? These, I mean, these are things that do not appear. These are things that do not get summed over in this Yang-Baxter, right? So in particular, so the point is that if I implement the sum, then what I get at the end is this power of Q times this left side over here, and then I sum over all possible boundary conditions that enter and exit through the left side. Okay, so the left side of the fused Yang-Baxter is going to basically give me of this fused Yang-Baxter is basically going to give me a sum involving some power of Q times this left side of the sort of trivial Yang-Baxter, the bundled Yang-Baxter. And if I similarly do the same thing on the other side, then the right side of this Yang-Baxter is going to be the same power of Q times the right side of the bundled Yang-Baxter, and then I again just sum over all possible boundary conditions. So yeah, this is sort of a sketch of how you prove the Yang-Baxter equation for these fused weights. Are there any? Yeah, I apologize. This is somewhat messier, but are there any questions about that? Okay, yeah, I mean, hopefully in Sketch, it's clear what to do, although the indices make it somewhat heavier. Okay, so I've tried to explain what the fused weights are. They're given by these sort of Q symmetrizations of these bundle weights. I've said so far that these fused weights satisfy a Q exchangeability, which allows you to define to define them. And I've also said that these fused weights satisfy the Yang-Baxter equation. But what I sort of owe you now is an explanation of how to compute them, of how to actually evaluate them. So, so a point that I want to make is that these fused weights can be evaluated recursively. There's a recursion that allows you to analyze them. So you can say, put them on a computer. You can compute these, implement the recursion, and this will give you, like, the computer will spit out formulas for these fused weights. If you're lucky, you can see a table of these fused weights and just guess the general solution to these to the recursion. Or you can just solve the recursion by hand if you want. And that will give you sort of a closed form answer for these fused weights in terms of all of your parameters, L, M, X, and Y. So let me explain how this recursion works, and then I'll tell you what the answer that you get is. Okay. So let me assume for simplicity that L is 1. So in this rectangle that I'm fusing, the height of the rectangle is 1 and the width is M. Okay, and we'll let M be arbitrary, but just for simplicity, let me set L to be 1. You can kind of do something fairly similar if L is arbitrary as well, but this will make notation much worse. Okay, so I have my fused weight RU of A, B, C, D, and by definition, I remind you, this is equal to a sum over Q to the number of inversions in A, basically, times the number of inversions in B, but L is actually 1 here, so B has no inversions. B is just a single number, so it has no inversions. Minus, okay, so then I have times Q to the minus the number of inversions in C, times again Q to the number of minus inversions in D, but again that's 0. So I have this formula over here, which describes me the fused weight. Okay. So okay, so I'm again, as I mentioned before, by Q exchangeability, I can pick any choice of C that I like here. Okay, I mean, it's independent of the choice of C. So actually using this, you can kind of come up with clever ways to compute these weights in special cases. But let me just give you sort of the most naive and straightforward way to compute these weights. So if the number of ones in C is at least 1, let me set C4 equal to 1. And if the number of C's is 0, then I'm stuck. I have to set C4 equal to 0. Okay, and let me suppose for the moment, for the sake of just exposition, let me assume that C is that the number of ones in C is at least 1. I mean, you can do something fairly similar if that number is 0. Okay, so in that case, I'm going to set my C4 equal to 1. Okay, and basically the point is that all I'm going to do is I'm going to pluck out this weight. I'm going to pluck out the leftmost vertex and sum over all possibilities of this edge K here. Okay, so right, so let me go ahead and do that basically. So I have on the left side I have this fused R weight. So on the right side, what I'm doing here is I'm just summing over all possibilities for A4. So I'm summing over A, so I have to sum over this A4 here, and I also have to sum over K. So I have 2 possibilities for A4 and 2 possibilities for K. So I have 4 things in the sum. I'll get something that looks like this. So let me maybe do 2 terms of the sum, and then I'll hope that you believe me on the other 2 terms. So this first term here is if I'm setting this A4 equal to 0 and K equal to 1. Okay. In that case, what I've done here is I've A4 is 0, and what I'm left with is a partition function. So I'm plucking out this leftmost vertex. I'm assuming that A4 is 0 and K is 1. And what I'm left with is some partition function for a row that has, again, A rows, A ones on the bottom, because I have not removed any ones. And now C minus 1 ones exiting through the top, because C4 was 1, I've removed one of the ones exiting from the top, and so I'm left with C minus 1 ones exiting from the top. And then the left boundary condition is 1. So this should actually be a 1, sorry. And the right boundary condition is D. Okay, so I'll get something like R of this weight over here times this fused weight, where I have one less arrow exiting from the top and the same number of arrows exiting from the bottom. Now you might wonder about this factor. Why do I have this Q to the C minus M? The reason is coming from this Q to the inversions sort of. right? So if this C4 is 1, then the number of inversions in this C, the number of inversions contributed by this C4 is equal to the number of zeros here, right? So I mean, you can sort of see that that's M minus C. So I have, yeah. Okay, so likewise, I can say compute. I can instead say sum over the. I can look at the next event that A4 is 1 and K is 1. In that case, it's almost the same as before, but now I've removed one arrow exiting from the bottom, so I only have A minus 1 arrows entering from the bottom. So I only have A minus 1 arrows entering here, and again I have C minus 1 arrows exiting here, which is why I have this weight A minus 1, C minus 1. Again, this should be a 1. And then I have some power of Q coming in from the top. Okay, I mean, you can kind of check through all cases. As you can see, I made various typos, but you can check through the cases, through all 4 possible cases of A4 and K, and you can write this fused weights in terms of fused weights of the small corresponding to a 1 smaller value of M. And you'll get some sort of recursion that relates this RU of ABCD of 1M in terms of RU of ABCD of 1M minus 1. So this gives you a recursion that will qualitatively look something like this. And the point is that you can solve this recursion explicitly, and the answer that you get is shown over here. Okay. Again, in the case when L is 1 and M is arbitrary. Okay, so right. So I'm taking the fused weight of R xy of A coming in from the bottom, some number B coming in from the left, some number C exiting through the top, and some number D exiting through the right. Okay. And this is equal. Okay, so I've sort of tabulated all possibilities for non-zero values of this vertex weight over here. And here is, you know, a formula for, as you can probably see, if you just plug in that previous recursion into a computer, you'll get this answer, and you'll get everything being fully factorized. So it should not be hard to imagine that if you just implement the previous recursion, you'll actually just be able to guess the answer and then use the recursion to check it. Although you can also kind of derive this in a somewhat more systematic way. But yeah, I mean, once you have the recursion, you're basically, in a sense, done in terms of computing these weights. Okay, so okay, now a few qualitative. Okay, so I've written down the weights fairly explicitly, but and I don't necessarily expect you to like memorize them or anything like that. But the 2 main points I want to make about them, 2 qualitative points I want to make about them, is that they're rational, or analytic, or actually rational in this parameter z, which is x over y. So first of all, they only depend on x and y through their quotient z, and they're actually analytic, or again even rational, in q to the minus m, or q to the m. So in particular, I can rename q to the m, and I can call that s to the minus 2, which is something we often do in this domain. And I can take my fused weights, and I can just let s. Now, originally s had to be q to the minus n, or more specifically, q to some minus integer, right? But these weights make perfect sense for arbitrary values of m. So in particular, I can just, once I have these weights for m integer, I can just analytically continue in q to the minus m, and I can just define them for any value of q to the minus m, and they'll just, all I've done from here to here is I've replaced every occurrence of q to the m with s to the minus 2. Okay, and I'll get weights that look like this now. Okay, and by analytic continuation, I mean, I write down the Yang-Baxter equation for these weights. It'll be some just polynomial expression in terms of x, y, and q to the m. If this polynomial expression has infinitely many zeros, right, in s, like if I take q to the m to be any integer value, any integer power of q, the Yang-Baxter equation will be satisfied, and therefore it will be satisfied for any value of q to the m. In particular, if I make s arbitrary. So in particular, that will imply, just again by analytic continuation, that the Yang-Baxter equation holds for these weights for any value of s. So this is sort of the final version of the fused weights when L is 1 and M is arbitrary. And as you can see, the parameter M is kind of hidden in this parameter S here. Okay. So it's a fairly general phenomenon that I should mention. I just did this all sort of in the case one of the UQSL2, but it happens fairly generally that these fused LM weights, they'll depend on X and Y only through the ratio like X over Y. And furthermore, they can be analytically continued in these parameters Q to the minus L and Q to the minus M, which in the literature we often refer to as R squared and S squared. Okay, so as you can see, there are sort of 4 parameters that underlie these weights. I have R squared, S squared, Z, and then Q. So these weights typically depend on 4 parameters. So are there any questions with sort of any of that story for the case of UQ SL2 hat? So, okay then. In that case, I will just mention a few sort of generalizations of that, and then I'll stop. So you can apply the same sort of qualitatively similar procedure, although it's a little bit more exhausting to implement, to the case of UQ of a quantum supergroup UQ SL hat MN. So this is sort of the quantum affine supergroup with superalgebra corresponding to SLMN, basically. So how this model works, how we think of this model is that there are m sort of bosonic colors and n fermionic colors. So any integer I between 0 and m minus 1 is going to be sort of bosonic color, and any integer j between m and n plus n minus 1 is going to be a sort of fermionic color. And the fundamental solutions to the Yang-Baxter equation for this model is given by this R matrix over here. So as you can see, if I is bosonic basically, then the weight, the fundamental R matrix gives weight 1 to the situation where I have all 4 states being the same and bosonic, but it gives a different weight, a slightly different weight to the case when all of the arrows are the same but fermionic. Okay. And then actually the other 4 weights are fairly similar to what you saw in the 6 vertex case. I think the difference is maybe I set u equal to y over x, but otherwise it's the same. Okay, so I have these fundamental R matrix, which is basically the image of the R matrix for UQSL hat MN under its defining or its fundamental representation. Okay. So these are very old weights. I mean, these go back to 1987, so 35 years old by the way. I mean, by this point, and it's been known since then that these weights satisfy the Yang-Baxter equation. Okay, so I can now apply fusion as I did before to these weights. I can again sort of take an L by M rectangle. I can set up boundary conditions along the bottom, left, right, top, and right. Apply fusion in the same way as I did before. Specialize the row spectral parameters to be in a geometric progression with ratio Q, as it happens once again that R of Q is a projection, so this is the right thing to do. I can specialize the vertical rapidity parameters again in a geometric progression with ratio Q. I apply this game as I did before, and I will get some sort of fused weights that more or less by abstract reasons satisfy the Yang-Baxter equation. Okay, and in this case, they'll be indexed by tuples, by a quadruple of tuples. So 4 tuples. And these tuples will now tell me, so I have like an A coming in from the bottom, a B coming in from the left, a C exiting from the top, and a D exiting through the right. Okay. And these tuples, these A, B, and C, D, they'll be n plus n minus 1 tuples. I'll use X to sort of index either A, B, C, or D. And here Xi is basically counting the number of arrows of color I along a given edge. So like, for example, AI counts the number, like A1 counts the number of arrows of color 1 that enter your vertex, and D10 count the number of the arrows of color 10 that sort of horizontally exit your vertex. Okay. So these are sort of the analogs of the state space for this UQSLM hat setting. Okay, so so if you define this Pockhammer symbol of AQK being the product of 1 minus A times Q to the J, and this phi to be it takes in two tuples, and then it sums xi times yj, where I is less than j. I'll give you a fairly explicit formula for this fused weight, which is shown which is shown over here. Okay, so I don't necessarily. Okay, so it's a little complicated, but I'll make a few quick points about it, which tell you maybe which might be sort of relevant. The first is that, as you can see again, L and M only find their way in this formula through being exponentiated by Q, by a power of, like, by seeing you only see an L and an M in the form of Q to the L or Q to the M. So for example, here this M is actually Q to the D to the minus DM. This L you can see is Q to the minus L or something like that. So these weights are once again analytic in Q to the minus M and Q to the minus L. Another thing which is fairly evident from the formula is that they only depend on X and Y through the ratio Z, it's X over Y. Okay. A few other properties of these weights is that this product here, it's telling you that the weight is only going to be non-zero if AJ, BJ, CJ, and ZJ are at most 1 for any fermionic color J. So for any J that's between M and M plus N minus 1. So what that means sort of qualitatively is that if I take any one of these fused weights and I look at any fermionic color, any edge can admit at most 1 arrow of any fermionic color, although it can admit as many edges as you want, as many arrows as you want of a bosonic color. And the last point I want to point out is that these weights are somewhat complicated. As you can see, they involve this sort of complicated sum. They're not fully factored. They involve this fairly complicated sum. But if you pick your parameters properly, you can actually rig it so that this thing does factor. For example, if this Z is equal to 1, then actually the sum is only supported on one entry. Okay, in which case this R weight will completely factor. Okay, and this will give rise to what's often known as this is closely related to the Q-Whittaker degeneration of this one. So let me just quickly mention a few special cases of these weights. They might look somewhat complicated, but the fact that I really have 4 parameters in the game, this L, M, Z, and Q, they make them, I have a lot of room to play. So you can specialize them to a lot of weights and symmetric functions and probabilistic models that people have considered before. So I'll give you a somewhat incomprehensive list, which is already fairly long. So okay, if Mn is 2, 0. Oh, wait, sorry. Okay, right. So before I do that, actually, how much time do I have, Slava?
You don't.
Oh, I'm out of time.
You're over time.
Oh,
Yeah, but I think you can finish the summary and the examples from the list because they're very important, I think. Okay, fine. Yeah. Okay. Sorry, I don't have a clock.
Right. So a few special cases. So if Mn is 2, 0, you can get the Holittle functions, their modified variants. Wave functions are eigenfunctions for A-SEP and Q-TAZERP. Also eigenfunctions for stochastic 6-vertex models. You can get the Q-Whittaker functions. If Mn is 1, 1, then you can get various Schur type polynomials such as factorial or supersymmetric or big Schur functions. Now, if Mn is if I set Q to the minus M to be 0 and basically Q to the minus L to be T inverse. So you should view this as kind of setting L to be 1 and M to be minus infinity. If I imagine that Q is less than 1, then you can get a fairly wide family of polynomials, including non-symmetric Hall-Littlewood, various types of multi-line Qs for A-SEP stationary measures. You can get certain families of non-symmetric and symmetric McDonald polynomials. You can also, these weights actually happen to be equivalent up to a Drinfeld twist to metaplectic or Iwahori p-adic Whittaker weights. Okay, and then right, and then if Q to the minus L and Q to the minus M are infinity and 0 in a sense, you can get various types of modified McDonald polynomials and LLT polynomials. So this is just some family of examples of special cases of these weights that give rise to important special functions. So okay, so I will conclude by just mentioning that fusion is a way of producing new solutions to the Yang-Baxter equation, starting from an initial one. The new solutions are often fairly general, and you can use them to get a bunch of well-studied symmetric functions that are useful in our analysis. These weights are basically defined by sums, like sort of Q sums of rectangular partition functions with specialized rapidities. In the simplest case, these rapidities are chosen to be in a geometric progression where the ratio is chosen so that the R matrix is a projection. And in these cases, some partition functions satisfy a certain form of Q exchangeability. And these fused weights satisfy a recursion, which basically allows you to solve for them explicitly. And this can be implemented, and you can get closed, but sometimes it's somewhat complicated formulas for these general fused weights that involve a lot of parameters. So I just showed you the example of UQ, SL, MN hat, and you can specialize these parameters to get all the new solutions to the Yang-Baxter equation. So for that, I'll thank you for your attention and apologize for going over.
Thank you so much. Let's thank the speaker.